Okay, so the last question kind of tripped me up, not gonna lie.
Like, did you get under 5 for one of the answers?
Yeah, I did.
Okay, I was just pretty sure because I felt like I got the whole overall, I think I got at least 3.
I looked at it, the undefined one, and I was like, because I didn't read like most of it. I didn't read the undefined part, so I was like, there's no answer.
I was looking at the graph then, I was like, wait, is that
I looked at the graph and I was just lost on that question. So I was like, it has to be undefined. There's no way it's.
You was it? The one that's all of the words.
I did pretty good though, but I didn't.
Yeah, I haven't even like done that yet because I'm like,
I'll try and end late for like a little bit less credit.
and then I have a question
It's
on
like
like my head homework.
it's like 20% less or something.
Yeah.
That's if you turned it in like a week after the due date, and it just slowly gets worse. You need to chapter 11.
Maybe we'll have to ask about that.
Oh no!
Did you pick up that stuff too, or was it?
I'm gonna grab some.
Come on.
Yeah, are you serious? They like were
Maybe if I would have studied that, would have gotten 100%.
Even if I did, even if I studied, I probably would have still got the same scores. So I probably got a low C. Or at least it. Oh.
I don't know, this was the test that I've been struggling on for like. I think I got a better score than last year.
Really?
Last year I got like 20% or something.
Oh wow.
Getting a B actually be way easier.
High or low or?
Read the question. It'd come up while you read it because you have to polish it and all that, like there's stuff about stuff on it.
Yeah, I said the magnesium. Oxygen.
Yeah.
And what about this one? This one I didn't read. Not for the magnesium. Oh yeah, I know. Yeah.
Well, probably high one.
Yeah, I said it right.
Yeah, these you think more oxygen came out.
Cool.
Wait, the oxygen in there? Or?
Yeah, that's kind of the only thing to do with it. That's what I got
All right, let's go ahead and get started. So don't forget to register.
Stuff added on it.
Yeah, but it seemed like there would be more percent oxygen.
Inside of it though?
So I think I saw like 11 people were registered so far for my Chem 222 class. So just keep registering since I think there's 36 of you approximately, and currently one lab section. So fill it up so that admin knows that yes, we need another lab section for you guys. So register ASAP, so it's a new week, so new people should be able to register. Is anyone not able to register this week? I don't know what your...
I thought it said like 38 or something more credits.
So 38 is like...
Oh, it's 20.
It's at 20
It's at
Is
20
it one
credits.
today? Okay. Yeah, 'cause last week it was like
So it's open now?
To everyone today.
Okay, so it should be open. If it's not, you can always email me too if you need help. So sign up. Let admin know that yes, we're all taking Chem 222. I don't want to lose anybody. And so y'all have been doing pretty well in this class, so just keep it up. Don't forget about those reading questions, the reading quizzes that are only online. And someone had asked me a question, and then I totally forgot to talk about it. So if you noticed, in like one of the weeks that has like the inner chapters, and so I posted an announcement. I don't know if y'all saw that. So I posted it as an announcement, so the link takes you to the inner chapters that it's talking about, so they're just more kind of fun facts about chemistry and history stuff. So that's where to find the inner chapters that it refers to. Oh, and then one more thing on the calendar. So coming up, I have planned a guest speaker for y'all. And so I'll probably do extra credit for that as well. So there'll be extra credit opportunity. And we did this last year with another person. And so it just so happens, so Molly, your sister, is currently in a graduate program doing chemistry research. And the funny thing is, so last year I also had a student with like a brother or sibling doing chemistry research. So this year we'll feature Molly's sister. I'm totally blanking on your sister's name. What's her name? Carly. So we'll have Carly speak. And what year in graduate school is she in? So she's a first-year graduate student, and so that'll help you get some perspective. What does it take to even go to grad school? What is she doing? And she's already doing like really cool research. She's already been involved in projects. And so that's why I keep encouraging y'all, like, sign up for research opportunities now. It is not too early. And so I'll say that again. So you have, right, all of December, what you can be thinking about. You got scholarships to apply to. Look for REUs, research opportunities. And so again, just email me. I don't officially work in December, but I'm definitely still around and I am available to y'all. I'm more than happy to help you so we can chat about that. Once you have some time in December to think about anything. And so back to registration, I would say if you need help registering or thinking about how to transfer, feel free to talk to me. You know, I've been in academia a long time, worked at a bunch of schools, so I know what I'm talking about when it's like, if you're a chem major, this is what you need to do. Because again, I've seen some bad advice given from the advisors here if they're not science people. So talk to your science folks. Talk to Dusty, talk to Corey too. They know how to transfer to the universities so they can give you the right advice. Anything else? Any other questions, comments, concerns? So let's start chapter 11 then. So chapter 11 is probably one of the most important chapters, since we mentioned one big thing about chemistry is you always need to know, well, how much am I weighing? How much am I reacting? How much should I expect? And so, of course, any reaction you do, that's what you're going to be doing. And so let's first define a mole. Have we gone over the mole derivation in this class? I feel like we have, but maybe we haven't. And so first let's go into, well, how did they even figure out this crazy number? And so let's just start off with what is a crazy number? And so a mole is defined as 6.022 times 10 to the 23rd. And so this could be atoms, molecules, or just things. So this is similar to like a baker's dozen, right? So if you say, or a dozen, so a baker's dozen would be 13, and that's all it means, right? So you have 13 atoms, molecules, things, so same thing with Avogadro's number. We have 6.022 times 10 to the 23rd atoms, molecules, or whatever thing. And so now let's go back. Well, how the heck do we even get this crazy number of 6.022? And so they based it off of carbon. So we go to our periodic table. So we have carbon here. And of course we know this mass is just the average mass, but they wanted to set, if we're looking at carbon 12, so we know the mass of carbon 12, or at least one atom, is 12 AMU. And so if we set up, so 12 AMU, we want to multiply it then by some factor. And we want to be able to get the same mass. So we want to be able to look at this periodic table, and we want to be able to say, okay, this is the mass of one atom, 12 atomic mass units, or it's the mass of 1 mole, 12 grams per mole. So they had to come up with some factor to get to this 12 grams. And so let's look at how to get there then, essentially. And so I was feeling a little lazy. So I just typed into Google, because the first step, of course, is we have to convert 12 atomic mass units to grams. And so this is going to be equal to 1.9926 times 10 to the negative 23rd grams. And so again, right, this is the mass of one atom of carbon, or of carbon 12. So we're just looking at that one isotope. And then, so now you're kind of seeing where Avogadro's number will come in. So there's our factor. We need to get to 12 grams. And so now if we divide, so 12 divided by this 1.9926 times 10 to the 23rd. And so look at what it gives us. So it gives us back Avogadro's number, so 6.022 times 10 to the 23rd. So there's our factor of x. So 6.022 times 10 to the 23rd, then atoms, molecules. So this is where that number derived from. So you may see some discrepancies too, like I've seen 6.021, 6.023, and so all that just comes from them trying to refine that number a little bit better. So of course getting very precise measurements of one atom to a mole and doing all that conversion. So that's where that factor comes in. So our mole then is just defined as 1 mole contains 6.022 times 10 to the 23rd, whatever of that is, so atoms, molecules. And so we know that the mole is also related to the mass here, so we know, again, we can add them up and just get our molar mass of anything. So it corresponds to mass on periodic table. And again, that's why we can say that our molecular weight, our molar weight for carbon is 12 grams, and then that's always per mole. So that's anything we read on the periodic table. So silicon, right, 28 grams per mole, or one atom is 28 atomic mass units. And so I think we've done this just in lab. It kind of has come up. But let's go over it formally so we're all on the same page. And so now with this convenient factor, we know our molecular mass. So we know the mass of an individual molecule or formula unit. And then we know that that's the same as 1 mole. So again, that would be in atomic mass units from our periodic table. And then the mole is always going to be in grams per mole. And then so, like I said, we probably have done this before in lab just because it's kind of unavoidable. As you've seen, this is a really important skill. So we can find the mass of either one molecule of H2O. And obviously you're going to have slightly different numbers with rounding. So in practice, most people just round like hydrogen to 1. You could leave it 1.008. You know, in this example, they rounded to 1.01, so there's going to be some rounding differences. But then we just add them up, so we're just adding up from the periodic table. So we have 2 hydrogens, so 2 times our mass of hydrogen plus then the mass of oxygen. And again, it's appropriate to round to 16. You could keep it 15.999. Most people in practice just round oxygen to 16 though. And so we get this number, so 18.02 atomic mass units. So again, one individual molecule weighs that. But then we know we could take this, convert this to grams, multiply it by Avogadro's number, and then we would get this factor. So 1 mole of water then is 18 grams per mole. And so let's do some practice, but before we get to the practice, so we'll go over conversion factors. So you can totally use your conversion factors to figure this all out. But I'm going to hand out this handy dandy mole highway chart, which is just a nice sanity check, so you can kind of double check yourself. Did you already grab some? And so let's do the first one together. So I'm going to show you with dimensional analysis, but then you can double check your sanity with the mole highway. So the first question is, so convert 35.55 grams of carbon to moles of carbon. And so we can set up, so we know carbon. So carbon, we have the molecular weight is 12 grams per mole. And so now we can start to see our conversion factor. And so begin with what you are starting with, so 35.55 grams. Then we're trying to go from grams to moles. So that's what we need in the end. So this is now our conversion factor. And so with our conversion factor, we need to put grams on bottom. So 12 grams goes on bottom. Moles goes on top. So that leaves us with moles for our unit. So now we can just divide. So 35.55 divided by 12, or 12.01. And so you should have 2.963. So 2.963 moles for 4 sig figs. And so if you look at the mole highway, it also tells you what to do. So we have our mole highway. So we're looking at it. It's telling us, okay, if we have mass, we want to go to moles. It's telling us divide by molecular weight to get moles. We did that. So that all made sense with dimensional analysis. And so that's a good sanity check. So now see if you can try this one. So a little bit tricky now, so we have to get the mass of silicon tetrachloride first. And so see if you can convert that then from moles to grams. So help me out with this one. So what do we get for the molecular weight of silicon tetrachloride? 169.898 grams per mole. So that looks good. So then we can set up what we know. So 0.227, so we have moles. We're trying to go to grams since it's talking about weight. So grams. And so if we just multiply it by the molecular weight. So notice how moles cancels out, leaving you with grams. And then we can check our sanity with our mole highway, check our dimensional analysis. So we're trying to go moles to grams. So it says multiply by molecular weight to get grams. That all checked out with our dimensional analysis. And so what do we get for the mass of 0.227 moles then of silicon tetrachloride? 38.5. So I'll round it to 35, or what did you say, 38.6? So I'll round it to there. So 3 sig figs to begin with. So this doesn't matter for sig figs. So 38.6 grams. All right, so now let's look at this next question. So it says, how many molecules of aspirin are there in 30 milligrams? So now just kind of thinking about what it's asking us to do. So we have grams, and we're trying to get to particles because it's asking about individual molecules. So looking at your mole highway, so we need to go from grams to moles to Avogadro's number. So you can kind of set that up in your mind. And then looking ahead at the next part, so then how many atoms of carbon are there? How many of oxygen? So how would you treat that? And look at the formula. So what does that mean? So I'll give everyone a couple of minutes to get started on that, and we'll go over it. I know you're probably not done, but let's at least start kind of going over it together. So what do we need to find out probably first to tackle this problem? So we need a mass of aspirin. So what do we get for that? $180, you said 0.159? And then, so thumbs up, did people get roughly this? Awesome. So we got this, so that's our first step. And so now we can set up, except we have 30 milligrams, so what should I do with this 30 milligrams? So convert it to grams, so 0.030 grams. And so now I can at least figure out how many moles and go from there. So we have grams. We can go to moles, so I'll divide by our mass. And so I could either punch it in and solve it here, or we can continue with our dimensional analysis. I'll do that just so we can all follow along. And so you get this for your amount of moles, roughly, so 1.66 times 10 to the -4th moles. And so what's the next step? So we're at moles. So multiply by Avogadro's number. And so you can set up, right, your conversion factor. So 6.022 times 10 to the 23rd. So molecules are in 1 mole. So then, just like you had said, we know we need to multiply so that moles cancels, and we're left with individual molecules. So times 6.022 times 10 to the 23rd. And so this gives us molecules of aspirin now. So 1.0 times 10 to the 20th. So now this is molecules of aspirin. So did we all get to this part at least? So I see a lot of nods, some no's. So do we know how to get here now? And so now that we're here, so this is where we could set up a proportion to answer the rest of the questions. And so now it's saying, so how many atoms of carbon are there? And so, you know, if it's easy enough, you can see it and multiply by 9. You can also set up just formally more of a conversion factor. So you can say, well, for every 1 molecule of aspirin, it contains 9 carbons. And again, I'm just setting it up this way so it's really explicit by dimensional analysis. On an exam, as long as I can follow your thought process, I try to be generous. So molecules, that means, so molecule will cancel, and 9 atoms of carbon on top. And so now this would give us 9 times 10 to the 20th molecules, or in this case, atoms of carbon. Then we can do the same thing, so it's asking for oxygen. So how many oxygen atoms? So what could we do to find oxygen atoms? So the same thing, so just take our new factor of 4 this time. 1.00 times 10 to the 20th. Molecules again for aspirin. And we'll multiply it by our 4 atoms of oxygen for every 1 molecule of aspirin to give us 4 times 10 to the 20th atoms of oxygen. So any questions about this? So again, I highly encourage the dimensional analysis just because it helps with all the unit canceling. But again, go back to your mole highway. That's why I gave it to you for a sanity check. And so we had mass, so we knew we needed, we're trying to get the particles from our problem, since it was asking about individual atoms. So we started with grams, had to get to individual. And of course, from our flow chart, we also saw that yes, we had to go to moles first. And so that's how we know that we need to go grams to moles and then to particles. And again, use these little hints so it tells you to multiply or divide appropriately, whichever way you're going. All right, questions about this problem before we move on? And so now we're going to look at basically what you did in lab, just kind of more practice and more complexities. And so this is actually a really, really powerful technique. And so this is related to elemental analysis. And so basically what happens in a research lab is you make your compound, you think you know what it is, you think it's really pure, but then you have to send it off to these companies that do this elemental analysis. They burn the crap out of it, and then they give you some sort of percent of, it's usually carbon, nitrogen, hydrogen, I can't remember if it's oxygen as well. But then they give you these percentages, and it has to be really, really precise. So there's standards that it has to meet, and you can only be off by a very small percentage. And why that is because it tells you the identity, and it also tells you how pure it is. So if you just give them a bunch of crap, even if your sample's in there, it won't hit. And so again, this is really important. It helps verify that you are actually making what you think you're making, since there are all sorts of ways which things can go wrong. And so let's see how you would do this. And so just like you saw with the magnesium oxide lab, so you got an appreciation of how to do this. Of course, in our chemical formula, we know that they are in relative whole number quantities of each element. And so we can determine the percentage just like you did in lab. So we can combust them and then figure out the percent composition of each. And so of course, things get a little tricky here, so we'll talk about rounding. So just like I was mentioning in our lab, that's why we don't want to round, like even if it's 1.3, we might want to multiply it by 3 to get to those whole number ratios. That would be too far to round. But we'll do some practices and it'll make hopefully more sense. Oh, sorry. And so the thing that we can get from our data too is, so we can only get the empirical formula, at least from this combustion analysis. So this just gives us the simplest whole number ratios. And so the empirical formula is different from the, let's say, molecular formula. So let's look at the difference. So the empirical formula is just going to be our whole number ratios. So for example, you could have some compound and determine it to be CH. You just know they're in a 1-to-1 ratio. But then if you had some additional data, so then you'd have to put it in like a mass spec or something, so you could see, well, what's my parent peak? What's the biggest mass? And so that's what would tell you the molecular formula. And so in this case, it might be C6H6. And so I'm just thinking about benzene in my mind here. So this is a good example of where you get your empirical formula and of course not the matching molecular. And so that's all we can determine. So again, just like you saw in lab, you divided and figured out your ratio of magnesium to oxygen. And so this can be determined from elemental analysis. So again, that's just where they burn the crap out of it and analyze what's left. And so the mass of elements formed when a compound is decomposed or react together to form a compound. And so we'll look at this. And again, our empirical formula represents our ratio of atoms, or a ratio of moles of atoms, so not a ratio of masses. And so all that means is, just like you did in lab, we converted to moles before we compared molecular weight, or molecular ratios. All right, so then we'll go through kind of the steps to go through it. So let's go to this. So let's look at our practice problem. So it says a compound containing nitrogen and oxygen is decomposed in the lab and produces 24.5 grams of nitrogen and 70 grams of oxygen. And so the first step on this, how to combine an empirical formula. So if they ever give it to you in a percent, you just assume you have 100 grams of that compound and convert your percentages to grams. So this is the easiest way. So looking at our problem, so they could have said, it gave you 24.5% nitrogen and 70% oxygen. Then we would have had to convert to grams. But in this case, they already gave it to us in grams. So that's okay. That's step one. So just, are we in grams? And then, so step two, you should kind of remember from your magnesium oxide lab. So now you're going to convert the mass to moles of each element. And so let's do that here. And we're just looking at individual atoms. So we need to divide by just one nitrogen. So 24.5 grams divided by the molecular weight, so about 14. So just pulling from the periodic table. So divided by 14 grams. So then this gives us moles of nitrogen, so 1.75 moles of nitrogen. So now do the same for oxygen. So do the same thing. So we had 70 grams, divide by 16, since that's a mass of one oxygen. So now I get 4.375, so moles of oxygen. And then, so the next part, so again, we should remember from our lab, hopefully, but now we divide by the smallest number of moles to get our whole number ratio. And so if it's within about 0.1 of a whole number, then rounding is okay. So really small tolerance. Otherwise, we'll multiply the ratio, so let's see what happens. So again, we just want to get our whole number ratio, so we want to divide by the smallest. So divide by smallest moles. So in this case, our nitrogen. So if we divide nitrogen by itself, so 1.75, of course, divided by 1.75, we get 1. Then for oxygen, so 4.375 divided by 1.75. And this is where you don't want to round until the very end, or at least try not to round, so keep as much as you can. So that will help you. So now we divide and get 2.5. And so this is a really nice example. So obviously 2.5, we're too far to round. But if we want to get our whole number ratios, we can multiply everything by 2 in this case. And so now this gives us a formula, or let's start with our ratio. So 2 to 5 for nitrogen and oxygen. And so this means we can write our formula then. So N2O5. So does that at least feel familiar, since we kind of did it in lab, got a little taste, so now we're just seeing. And so this would be technically, right, your empirical formula. We don't know if it's a molecular formula, so this is where we'd have to shoot it again through our mass spec. Does it actually match with this? And so what you'd be seeing, so 14 plus 14 plus 5 times 16. So this has a mass of 108 grams per mole. So then you would shoot it through the mass spec. Do you see a peak at 108 grams per mole? If you did, then you would know, okay, yes, this is my molecular formula. But what could also happen is you could shoot it through the mass spec. So let's say you shoot it through the mass spec. And you'd have to get some sort of ratio of this, so you can't have, like you couldn't do 108 times a half of equivalent, so times 1.5. So you would never get like 162. That wouldn't make sense. But you could have, so if it was actually doubled, so maybe you got 216, you shot it through the mass spec, it came up with that mass, then you would know, oh, okay, I need to multiply this empirical formula by 2. And that would mean your actual formula is N4O10. And so that would be your molecular formula. And so looking at this, so now this is just the text to explain it. So like we were seeing, the molecular formula is a multiple of the empirical formula. So again, it's the actual, what is the compound physically bound to, what does it look like? And so of course, if we know the formula, we can determine the mass. And so like we saw, the molecular formula is just your empirical formula times whatever integer would be. And so that's where you have some sort of extra information from, like I said, the mass spec to figure out your true molecular formula. And so in this case, right, what if it had been, so if you did 108 times 3, so that could also be appropriate as long as it's some whole number factor. So then you know you need to multiply this whole thing, N2O5, by 3. So I'll just write that out. So we got N2O5, molecular weight is 108 grams per mole. And if our mass spec had then showed 324 grams, so then you just multiply, so 320, or divide, so 324 divided by our 108 takes you back to your 3, so you know what your integer is, and that means you can take then our N2O5 times 3 now for our imaginary scenario, and so that would be your new empirical formula.
The mass spec number, is that like where the peak is, or like what? I guess I don't understand what that number, where that number comes from.
So in like a problem, it would just be given to you. Like we shot this compound through the mass spec and it showed a parent peak at 324. And so let's kind of answer your question more. Oops, that's not what I wanted to do. I love it. And so in a mass spectrum here, so just looking at like this formula, so we see the parent peak. So that's called the parent peak. And so this peak corresponds to your highest mass of your molecule. So that's what would be given to you. So does that make?
And so that's the max spec number is the weight, I guess, of the most weighted molecule.
Yeah, so it'd be like your biggest mass. So that your parent peak should correspond to like the compound.
Okay.
So it's basically like your parent peak is the one with the highest mass. It's not necessarily the largest because they tend to break up, but whatever is the highest one you see, you look at it and you go, okay, that is what my unit is. That's my biggest unit intact. And so that tells you, again, what the mass is. Let me see if I can find a massive. Oh, come on. Sorry, I was trying to find a mass spec of N2O5. It's not always easy. Let's find benzene. That's kind of easier. Okay, let's look at another one that we talked about. So this is benzene. So what I was rambling about, that benzene, you would only get a 1-to-1 CH ratio. But then, so if you look at the mass spectrum of benzene, so it looks like a mess. But then what you care about is kind of, well, what are the largest parent peaks here? So you have either 78 or 79 because you have isotopes effect. So you would probably pick 78. So let's go back to our kind of example here. So now, let's say we're looking at benzene. And let's just say we determined that CH is the empirical formula. So that's all that you could determine just from the ratios. But then in a word problem, it would probably be something like 78 is the parent peak, or something like that. 78 is what the mass corresponds to. And so you wouldn't be looking at this on an exam, but that's how you would determine it. So that's where that number comes from, 78. And then you would say, well, what is the molecular formula? And so that's where you find your mass of just your empirical formula. So this would be 13 grams per mole. And so what's 78 divided by 13? That gives us 6. So now I know, okay, well, let me take this CH, multiply it by 6 then, so I know it's C6H6. And so that corresponds to what benzene actually is, and that matches with that mass spec. Yeah, great questions, because this is all really relevant to like doing research and confirming what you made. Like this is super important in being able to put all these pieces together. All right, other questions on that and how that all relates? All right, so let's look at more combustion analysis. So like I mentioned, this elemental analysis is a very common technique, and so usually it just gives you either carbon, hydrogen, or oxygen, or like I mentioned, sometimes nitrogen from the companies. And so now here are some kind of helpful hints to help you with these combustion analysis problems. And so it says, right now we have to determine, based upon, you're going to get some products. And so those products, let's just go through thought experiment. What is a combustion? So we mentioned, so we have some sort of hydrocarbon, so C something, H something, potentially oxygen, so it doesn't always have to contain oxygen. Then plus oxygen in some equivalent, so we don't know, always gives us CO2 and always gives us water. And so now the question is, well, if we are given the amounts of CO2 in water form, can we go back and figure out the problem, or the original hydrocarbon? And so now kind of the key hints are in this little statement here. So all the original carbon forms CO2. So that makes sense, right? The oxygen's not bringing any carbon atoms in. So however many carbon atoms we had here, that will give us how many carbon atoms are in CO2. So that helps us. And then the hydrogen forms H2. And so we're going to have a little bit of factor to deal with. So we have, of course, our hydrogen becomes H2. So we can multiply this and get back how many atoms of hydrogen we had. And then the original mass of oxygen is found by subtraction. So that means we're going to have to find the mass. So find mass of carbon and hydrogen in original sample. And then we'll be able to determine how much oxygen is left. And then once we get all that, it'll be the same thing. So once you get to all the masses, you'll get to moles, divide by ratios, and get our empirical formula. So let's do that together. And so this is just a little schematic of how these combustion analyses are run. And so what's really cool is if you have an air-sensitive sample too, they are able to handle that. I think they take it into their glove box and prepare it. And so they put it into their furnace, obviously add oxygen. Then there's a water absorber and CO2 absorber. And so then they can weigh the products and again figure out your ratio of hydrogen and carbon. So let's look at our example. So it says, upon combustion, a compound containing, well, at least this helps us, so it contains only carbon and hydrogen, produces 1.83 grams of CO2 and 0.901 grams of water. So now determine the empirical formula. And so again, I'm just going to rewrite our general form so we can remind ourselves where things are coming from. So obviously this isn't balanced. And so, like it said, all the carbon in CO2 corresponds to how many carbons there are. So let's figure out how many moles of carbon. And before we even get to moles of carbon, we have to get moles of CO2. So let's do that. So what's our molecular weight of carbon dioxide? Well, 12 plus 16 times 2. So what's our molecular weight of CO2? So 44 grams per mole. And so now step one, just figuring out moles of CO2, so we can just divide. So divided by 44. And so now we have 0.0416 moles of CO2. Except we need moles of carbon, right? But in this case, for every 1 mole of CO2, it contains 1 mole of carbon. So then we can say, well, I have 0.0416 moles of carbon in our original sample. So I'll just highlight that for now. We'll go back to that later. So then second step, so we need to get how many moles of hydrogen we have. So let's figure out, so they gave us grams of water. So now we'll do the same thing, go from grams to moles of H2O. So we'd started with 0.901 grams of water. And then what's the molecular weight of H2O? So 18 grams per mole. So 1 mole, 18. So divide. So now we have 0.05, and I guess I'll leave it there, moles of H2O. Except in this case, so how many atoms of hydrogen do we have in moles of water? So 2. So I'll write it out explicitly. So for every 1 mole of water, we have 2 moles of hydrogen. So in this case, we need to multiply by 2. So don't forget that. So now times 2. So that gives me 0.1 moles of water. Yeah, I'll leave it there with rounding. Oops, that's not what I meant to do. So 0.1 moles of hydrogen, sorry. And so now we're kind of at that last step. So now we have moles of carbon, moles of hydrogen. So just like we did before, we can divide by the smallest to get our mole-mole ratios. Now divide by smallest. So in this case, looks like our carbon. So and so now just find the ratio. So 0.0416, obviously divided by itself, gives us 1. And then for hydrogen, I have 0.1 moles. So divided by 0.0416. Let's see what the calculator spits out. So this is a little awkward one. So now we get 2.4. And so this is where kind of judgment calls can come into play, and you want to show your work. So looking at 2.4, can you think of a number that you could multiply by to give us a nice whole number? So 5, so I would go with that as kind of the best answer. So you could go times 5, and so that gives us a nice ratio. That gives us 12 for hydrogen, so we get C5H12. So this is really kind of, I'll put best answer, at least given our numbers here. And so if you had decided, maybe 2.4, that's kind of close to 2.5, I'll just multiply it by 2 and round to, C2H5. So this would be okay, not the greatest. Obviously, you're going to have different answers with rounding potentially, But just, this is where showing your work is really important, so just show your work, and, I will make sense of it, type of thing. And so you would, again, need more information to figure out, yes, is this my best answer? So that's where the mass spec comes into play. You would have to shoot it through, and maybe it'd give you a parent peak that kind of helps you figure out, well, which is truly the correct answer. But for our purposes, again, I expect some discrepancies potentially. So does that clarify things? So again, just show your work, show your work, show your work, and I can give you credit.
So you multiply the moles of CO2 by what to get moles of carbon?
Just by 1, because in that factor, since we just have a 1, so for every 1 mole of CO2, you just have 1 mole of carbon. And you could think of it, right, its subscript here is 1, so that's what you multiply it by. And then hydrogen, so of course its subscript is 2. That's where we got the whole ratio. For every 1 mole of water, you have 2 atoms of hydrogen, and that's why we multiplied that one by 2. Other questions on this one? So now let's do it again, but now we have a sample containing carbon, hydrogen, and oxygen. And so I'm going to let you loose for a few minutes, see if you can get started, and at least maybe get to moles of carbon and hydrogen, and then we'll go from there. So we have, upon combustion, we have a 0.8233 gram sample of a compound. So again, it contains carbon, hydrogen, and now oxygen. And we react it and produce CO2 and water in the following grams. So can we determine our empirical formula? So let's at least see where everyone's at. So what did y'all do first here?
I found the moles of carbon dioxide.
Yeah.
So I heard several people say, so find moles of carbon, which we need from our carbon dioxide, so that sounds good. And so we said our molecular weight was our 44 grams per mole. So divide. So how many moles of CO2 did we get?
0.0556.
0.0556. I see some nods, so I'll roll with that. So moles of CO2, which then gives us moles of carbon, right? So they're in a 1-to-1 ratio, so 0.0556 moles of carbon. So that looks good. So what can I do next?
But you have to find the moles of oxygen in that too.
So we need moles of oxygen, but we'll get there.
The moles of water.
So let's find the moles of water. So moles of H2O. So then we had 0.6003 grams of water. So divide by 18. So what do we get for moles?
0.03335, but then you have to multiply by 2.
So 0.033 moles of water. And just repeating what she said, so multiply by 2, since we have 2 moles of hydrogen in every mole of water. So then we get 0.0666, repeating or so, moles of hydrogen. So this is good. So how do we get oxygen, though? So we have to subtract. Except what do I do with these numbers? How do I know what to subtract? So we have our original sample.
Would you add those two numbers together and subtract that from the original sample to find what oxygen is?
So add these two. So essentially, except we just have to convert them back to grams. So that's the only thing. So I like what you're thinking though. So 0.8233. And so now we have our moles that are in the original sample. So let's just emphasize. So this is moles in original. So now we need to go from moles to mass. So we can have, what's the mass of carbon in our original sample? What's the mass of hydrogen? And so let's do that. So 0.0556 moles for carbon. So times 12 now, since we just care about carbon. And then of course do the same for hydrogen, which would be the same number. So 0.0667 moles of hydrogen, so times its mass. And so I get 0.6672 grams of carbon in the original. Is that what other people got roughly? And so now to find mass of oxygen, so now we have to subtract. So 0.8233 minus the mass of carbon that we found, minus the mass of hydrogen. And so I get this number for the mass of oxygen in our original sample. So 0.0894, is that what other people got? See at least some nods. So 0.0894. So this is grams of oxygen. And so now we need to go from grams of oxygen to moles, because we still have to get a mole-mole ratio. So 0.0894 grams divided by 16, because that's a mass of 1 oxygen. And so now we get 0.00558 moles, or 0.00, I'll round to 559, 0.00559 moles of oxygen. And so now that we're finally here, we can do the last step of dividing by the smallest. So I'm just going to highlight, so we had moles of carbon, moles of hydrogen, moles of oxygen, so we know what we're comparing. And so just like we've done in the past, let's divide by our smallest mole. So in this case, it would be oxygen. Trying to show everything. So carbon, hydrogen, oxygen. So oxygen, of course, is just 1 divided by itself. And if we do carbon, so we had determined 0.0556 divided by this 0.00559. Oh. So I get a ratio of like 9.9 or so, or I'm probably going to round that one to 10. I'm feeling okay about that. Hopefully I don't regret it. And then divide the last one, so 0.0667 divided by our moles of oxygen. And so that's pretty darn close to 12, so I'll probably round to 12 for that one. And so this seems pretty reasonable for my formula. So C10H12O is in our formula. And again, we would need further information to figure out, is this truly our molecular formula? So again, right now this is just our empirical. That's the most we could get. We'd have to shoot it in a mass spec. And so just emphasizing its parent mass, so 10 times 12 plus 12 plus 16. So the mass of this whole thing comes out to 148 grams per mole. And so again, you shoot it in the mass spec, you would see, is it 148 or is it a multiple of 148? That would be the only last bit of that one. All right, so questions on that? It's kind of a lot. So again, just hitting the highlights where people go wrong. So just make sure you multiply by 2. People were pretty good about that. So just for your hydrogens. And then, of course, going back, once you get moles of carbon and hydrogen, go back to mass. So we can get mass in our original and then find that factor of oxygen. And then, of course, we just divide it by the smallest. We've been doing that. Feel pretty good about that. All right. Any questions on this? So we'll probably go ahead and end here for the day. So just looking ahead, we'll do some more reaction stoichiometry. So then figuring out how much can we make from a certain amount of moles, a certain amount of mass. And so stoichiometry is super important, and we'll continue with that on Thursday. So I'll see half of you in lab, so don't forget I think it's our last lab this week, isn't it? I think so.
Next week is our practical thing.
Yeah, and that'll be hopefully relatively easy. So yeah, this week is the last week of lab. Oh, and I forgot to say, I didn't actually tell you when we're having our guest speaker. I have too much ADD. And so the guest speaker is going to be December 2nd at 1 p.m. And so it'll probably be in HEC 112. But I will also put it up on Blackboard, so if you can't attend at this time, I would just ask you to watch it and write a quick 1 or 2 sentences. I like this about the talk, and that'll be your extra credit.
How do I get there off of Blackboard? 'Cause I'm
So I'll post a link to the video. So just like I do with the YouTube videos, I'll do a link thing, and then you can watch it.
Great event posted yet.
Yeah, because like that was just like a word now.
Oh, and then I forgot, I have homework. I didn't give you my homework. So if you want homework,
That was just like a
grab
word
it all
call.
the way out, or I'll have them in lab.
Word calls to the card.